Sorry.
Okay, good. All right. So yeah, then our next speaker is Bernardo Fraiman from IFT and CERN, and he's gonna tell us about rank reduction in non-supersymmetric string theory. So please, Bernardo, go ahead.
Okay, thank you very much, Alvaro, and also I would like to thank Matilda and Damian for the opportunity to speak here in this very nice seminars. I would like to tell you about some upcoming work we are finishing with Hector Parra de Freitas. We are very excited about. And also I will review a bit this paper of last year with Mariana, Hector, and Sab. So the title is Rank Reduction in Non-Supersymmetric String Theory. So I will try to motivate first the non-supersymmetric part and then the rank reduction part. So why non-supersymmetry? Well, when there is supersymmetry, first of all, this has been heavily studied in the last decades, but most of it is still unknown. But nonetheless, there is the underlying structure when the number of space-time dimensions is high, and when there is a big number of supercharges, especially for 32 and 16 supercharges. If one assumes a string universality, this is very interesting from a swampland perspective, because what is not allowed by this structure should automatically be in the swampland, so it should be rolled out by some conjecture. But until now, most of the effort has been put in the supersymmetric landscape. So what happens if all these nice structures that was found and all these nice properties and all the relation with the swampland is just a supersymmetric lamppost effect? So for this reason, it would be nice to break supersymmetry, and also, of course, at some point to connect more with phenomenology. So there is a way of breaking supersymmetry at the string scale. An example is the heterotic 10-dimensional of 16 string. And recently, there's been a recent resurgence in interest in this type of compactifications. This is just a non-exhaustive list for papers of the last years. The thing is that what I want to convince you now is that most of the structure that appears in the supersymmetric landscape for big number supercharges is preserved under this type of non-supersymmetric breakings. And something nice is that for each dimension, we will see that there are more possible compactifications, and also the spectra of particles is richer. And there are, of course, some issues because these theories don't have a supersymmetry, so they can have tachyons for some values of the parameter in the parameter space, but they do not appear everywhere in some of the theories. There's also a runaway one-loop potential for the dilaton, but doing constructions like the one on this paper, one can stabilize the dilaton, and in principle, we can get non-supersymmetric ADS solutions. In the paper of last year that I will review a bit today, many extrema was found for this potential, but until now there is no minima in the 016 compactifications. The thing is that when one compactifies on circles and then on tori of higher dimensions, we get each time more and more moduli. And this moduli sometimes is not very good because it gives more possibilities for the potential to don't be at a minima, because there are directions where it can decrease. But there are compactifications on orbifolds which kill some of the moduli, so we have less variables in the moduli space. And this is nice because then these theories are more likely to have stable points, and also it's easier to classify all the possible stable points because there are because the moduli space itself has less dimensions. An example is the CHL string that I will just tell you in a slide what it is. Like long ago, like in the beginning of this millennia, there was done in this nice paper by De Boer, Set et al. A systematic study of the supersymmetric vacua, like top-down constructions. But in the non-supersymmetric case, there's been very little. Last year, there was by Nakashima found a new non-supersymmetric theory which has reduced rank, but a systematic approach was not taken. So since, as I told you before, some properties of the supersymmetric landscape can be generalized to non-supersymmetric compactifications, what we want to do in this upcoming work is to do a systematic approach for these non-supersymmetric theories. So for this talk, I will focus on 9 dimensions, but the work is done in 8 and less dimensions also, but 9 dimensions is always simpler. So if we start with heterotic strings, we know that we have 10 space-time dimensions. We have supersymmetry and the gauge symmetries that are of rank 16. So there are different types of compactifications. If we do a circle, we have a theory with 9 dimensions, and the rank now is 17, and we have 17 moduli. It's possible to compactify using an holonomy that involves the space-time fermion number, and then we can break supersymmetry, but the number of moduli is still 17. And there's also the construction by Chadhuri and Polchinski, where one can compactify in a Z2 orbifold and break the number of moduli to 9, but this retains the supersymmetry. And finally, there are theories where one can apply a Z2 orbifold and also an holonomy that breaks the SUSY. So we get 9 moduli and no supersymmetry. In principle, the rank can be reduced even more, but I'm focusing on the simplest case. So to obtain all the possibilities here, one also has to consider 10-dimensional theories that have no supersymmetry from the start, and also a theory called E8 string, which has reduced rank from the start and no supersymmetry. So in the first part of this talk, I will briefly reduce a heterotic string on a circle just to explain some basic things. Then I will focus on the O16 non-supersymmetric string on a circle, explained in this paper. Then I will just flash some facts about the CHS string, which was also reviewed by Veronica in the last seminar of String Pheno. And finally, I will tell you about this rank-reduced non-supersymmetric theories, which is work in progress. So the heterotic string on a circle is a theory in 9 space-time dimensions. It has 17 moduli, which are the radius r and the Wilson line, which encodes 16 variables. The moduli space is just this coset, where this group here is just the T-duality group of the theory. And this is just a slice of the moduli space where we see that for generic points, we have like these white regions are just abelian symmetries. But when we stand in specific regions of moduli space, we have an enhancement to non-abelian gauge groups. So the different colors represent different symmetries. And something that happens because we have supersymmetry is that for each boson, we will have one fermion. So we have the graviton, and then we will have the gravitino. And for each gauge boson, we will have fermions called gauginos. So everything is relatively simple, but this is because of supersymmetry. We will see that this will change later when we break it. So each state can be characterized by some integer number, the momentum and the winding W, and some gauge charge pi, which is a 16-dimensional vector. And all of this can be encoded very nicely in the Narain lattice, which is a Lorentzian even self-dual lattice. This moduli space can be described by an extended linking diagram. I will not enter too much into details. I will just show you how this helps. The presence of each node means that we are in a region of the moduli space which is fixed in some of the T-duality. So this will give enhancement of symmetry. So if we delete nodes, we can get all the possible enhancements of symmetry. For example, deleting 2, we get the maximal enhancements. Here we get SU18, E8 times SU2 times E8. And in total, we see that there are 44 maximal enhancements. Like the number of nodes gives the rank of the symmetry, and the maximal enhancements are the symmetries of rank 17. Also, this extending linking diagrams encodes the compactification limits, because if one, for example, removes these two nodes on top, one gets this diagram down here, which is the affinization of the D16 of SO32. And if one removes the node in the center, we get E8 affine, E8 affine. And these two possibilities correspond to points at infinity. And these affine algebras can be found when doing an analysis like the one done in this paper. So this extending diagram already gives information about all the compactification limits. Okay, now I will break supersymmetry in the simplest way, which is the O16 on a heterotic string. This is defined as the E88 theory with some holonomy that breaks the supersymmetry by with this factor, which is +1 or -1, depending if we are on the Navier-Schwarz or the Ramon sector. And also we have to apply an order 2 shift in the internal lattice, with this pi being the gauge charge I showed you before. So the result is that this breaks supersymmetry, but the classical module space still looks very similar to the heterotic string. We also have the radius and the Wilson line, and actually the coset here is almost the same, but now the T-duality group here is different. So we will have a different extended linking diagram, different fundamental region. And of course, the gauge enhancement will be different. Also, a difference is that the theory will decouple in 4 different sectors, like each state will belong to different classes. So the gauge bosons will appear at boundaries, but the fermions will not appear in that boundaries. And also the scalars will appear, will be quantized differently. And these scalars are the ones that can become tachyonic. This is just an example of some slice. This is for fixed radius, and the horizontal and vertical directions are the subcomponents of the Wilson line. We see that the massless bosons appear at these pull lines, the yellow and cyan, and they are boundaries of fundamental region, but the massless fermions appear at these dotted lines, which are no boundaries in principle. And if we change the radius, we have this nice situation where we see that the structure gets more and more complicated. This is because when we have lower radius, we have states with more winding, which can become massless. But the thing is that it has a lot of symmetry, so there should be an easier way to study it. Another feature is that there are tachyons in part of the smaller spaces. This is because the mass of the scalars can be written like this, with PR the internal momentum of the states. So if this is equal to 1, we have massless scalars, which are shown here in this orange ellipse. But if PR squared is lower than 1, then we have tachyons. So we have that inside the ellipse, there will always be tachyons. Their mass will go lower each time we go to a center. And if we go out, we will have a massive scalars. So this is a generic feature of all these theories. Well, another thing is that since there is no supersymmetry, the partition function does not vanish, and then there is a quantum potential for the moduli. One can compute the one-loop partition function, the one-loop integral of the partition function, and then one gets this thing which can be interpreted as a cosmological constant or as a potential for the dilaton. The thing is that boson fermions and scalars, even if they are not massless, give finite contributions, but tachyons make it diverge. So we can analyze this only in the regions where there are no tachyons. This is just an example of how the potential looks in some slice of a model space. We see that the maximal enhancements appear always at points which extremize the cosmological constant. This will be important for searching stable points. And also we see that at the points of infinite distance, like radius 0 below and radius infinity above, the potential diverges. And in this case, this corresponds to the compactification limits to a 10-dimensional O16 string. Well, the nice thing is in this paper of last year, we found an extended linking diagram, which, just as in the supersymmetric case, encodes all the possible symmetries. So we have a total of 107 maximal enhancements. And the thing is that most of them are tachyonic, but there are 8 which are free of tachyons, which are analyzed here. They all have positive cosmological constants. The ones in green are saddle points. The one in blue is a maximum. And the ones in red are knife edge because they have massless scalars, so they just live at the edge of one of these ellipses. So when we move in some of the directions, the potential will blow up. The situation is that they are all unstable, but they all satisfy the refined de Sitter conjecture. This can be checked by computing the Hessian, and one sees that the constant C is of order 1. This is nice, but to find stable points, An alternative will be to go to lower dimensional compactification where there is much more structure. And this is a work in progress we have with Hector and Mariana. The infinite distant limits can be found also by just looking at different sub diagrams which are affine. These are all the possibilities, and in total there are 8 of them. They are also pointed here in these slices. The next thing is that these 8 points at infinity give the compactification to each of the supersymmetric and non-supersymmetric theories in 10 dimensions. In particular, there are some limits which restore supersymmetry. And this is very nice to analyze, because also the curves that connect these points at infinity are geodesics. In some upcoming work with Nacho and Irene, we are analyzing the behavior in these asymptotic limits of the tower of states becoming massless, which are also related to these affine symmetries that appear, and also studying these as interpolated models between 10-dimensional theories. Okay, so now let's try to reduce the rank of these theories to get less moduli and see if we can find new things. The CHS string was already reviewed by Veronica last seminar, so I will just mention that one can build it by taking the HE string, the E88 heterotic string, on a circle and putting on the circle an set2 holonomy, which consists of exchanging both E8 factors and then doing a half turn around the circle. While doing this, supersymmetry is preserved, but now the Wilson line gets projected into the region where it is invariant under the holonomy. So effectively, we will have just 9 moduli, the radius, and just 8 components of the Wilson line. So the rank gets reduced and also a number of moduli. This is nice. And then the states are just a bit more complicated, but we can use the same tools to analyze them. Now there are untwisted states, which are the original states that survive the projection. And there are also twisted states which have half integer winding. Here there is also an extended linking diagram shown here. And there's also a charge lattice analogous to an Arine lattice found by Mikhailov in the 90s. Here, by removing nodes, we can find all the 9 maximal enhancements. And also, we see that there is only one point at infinity, which should appear at the end of this animation. This point here is an E8 affine, and this gives the computation limits to the supersymmetric E88 string. This was explained nicely by in the last paper by Veronica and Hilarion. So this is just a graph to show you, like in one picture, how is the moduli space of CHS string. This red point is the point at infinity, and the black points are the maximal enhancements. And these connections are just the symmetries of the geodesic shown in them. This is just to show that we can show all the maximal enhancement in just one picture. So now let's break supersymmetry and reduce rank at the same time. In 10 dimensions, there is a theory which already has a rank less than 16, which is the E8 string, and it has no supersymmetry, but this theory is tachyonic, like in the bosonic string. It has states with mass square negative. But it will be interesting to analyze it. A way of constructing it is doing a set2 orbifold of the supersymmetric string. It's just exchanging the both EX, but now the rotation is done in the space-time. This is why we can stay in 10 dimensions. If we compactify in a circle, we will get a moduli space with 9 moduli, but it has generic tachyons. So it looks like this. It's like all this red region means that there are tachyons everywhere. But something nice that we found when doing this type of analysis is that there is a point here which has an affine U16 symmetry, but it's not just an affine, it's affine, twisted affine. It's like it's the type of symmetry that Veronica told us about the last seminar. The thing is that this showcases the compactification limits to a 10-dimensional U16 string. This was not known, so there should be a T-dual description of this moduli space by starting with this theory and doing some asymmetric Orbifold. If we put this theory on a circle, we also can build an extended linking diagram, the one shown here, and if we remove nodes one at a time, we also find that there are 8 maximal enhancements. Now we have also this doubly laced groups because there is a double connection here. And we see that there are 2 points at infinity with symmetries E8 affine and this A15, and this correspond to these 2 theories that I was I was telling you about. Well, okay, with supersymmetry, we have only one theory with rank reduced by 8, which is the CHL string. Without supersymmetry, there are 3 of them. The one that was known before was the E8 string on a circle, but very recently, the other 2 were discovered. One is the O16 string, and the other is the E7 times SU2 string. For lack of time, I will tell you only about the O16 string, which is more promising than the other. The way of building is very similar to the CHL. We just take the O16 string and apply a set2 holonomy which changes both O16 factors and does a half turn around the circle. So the rank gets reduced by 8 and also the moduli. And this theory has no generic tachyons. So the slides look something like this. We have some red region tachyonic, but the white region is free of tachyons. And this will be part of the upcoming work. So we also found an extended linking diagram, which was something non-trivial. And by removing nodes, we also find that there are 7 maximal enhancements, which are pointed here in black. But the very nice feature is that there are 3 points at infinity, which are these ones here. And there is one which has symmetry D8 affine. This is just the compactification to the original O16 string that is expected. But these 2 here have the same symmetry. But when one analyzes the spectra close to them, one sees that one has tachyons and the other doesn't have tachyons. So are these points equivalent or not? To understand this, we can look at this 3-dimensional slice of the mole space. The radius is the vertical direction, and the x and y just describe the Wilson line. All these surfaces are different regions of enhancement, and also these curves symmetries are here. The thing is that these 3 points at a radius 0, they are the compactification limits. And while studying how the partition function changes when going to these points, one finds that one corresponds to the O16 string, and the other 2 corresponds, one to the supersymmetric E88 string, and the other to the tachyonic non-supersymmetric E8 string. So we see that we can find a connection between these theories by just taking these infinite distance limits. So there should be a T-dual description of this as an E8 string compactifying an asymmetric orbifold, and this should be dual to theories already described recently. Okay, just to finalize, let me tell you about the one loop potential in this theory. One can do the same analysis we did for the O16 string for this case. Now there are only 7 maximal enhancements in 9 dimensions, and only 2 are tachyon-free, which have these gauge symmetries, SO16, SO2, and SO18. We see that the values of the Commosian constant are of the same order of magnitude as in the 9-dimensional O16 string. This is a nice fact, because now we have more control when we go to lower dimensions, where one of these points has massless scalar, so it lives at a knife edge, but the other has no massless scalar. But one can see that this is not a minimum in all the directions. But in principle, it could be used to construct stable vacua as with the tools on this paper. So the situation is that when we go to lower dimensions, there will be many more possibilities, and we already find a lot of points we have no tachyons, and since the number of moduli is less than for the full rank theories, this is very promising, so stay tuned for news about this. So this is just to summarize. If we write all the theories in 10 dimensions in the first row here, without supersymmetry, and all the theories in 9 dimensions that we were describing here, we see that there is a very nice web that interrelates all of them to find all these connections. One can start from 10-dimensional theories and find ways of compactifying, but also one can just take the partition function of these 9-dimensional theories, take limits, and see what theories appear. So we can find many unexpected connections, and we have this nice picture. Well, here there are the extended linking diagrams we found for these theories, which are called overextended linking diagrams, and they are also classified. So there seems to be a nice mathematical connection here. So let me just mention that when one does a sharp reduction of the CHS string, one gets a theory which is in a dimension which is not dual to the cyclic commodification of the others. So this should be a different one, and this has no generic tachyons. So to conclude, we studied the behavior of one loop potential for certain non-supersymmetric strings, and we saw that there is no minima, at least for the cases we check. If one does Orbifold compactifications, there is fewer moduli, so in principle they could be easier to stabilize. Until now, there is no minima, but this is work in progress, so stay tuned. In this talk, I only focus on 9 dimensions. For 8 dimensions and less, one needs to use exploration algorithms. We know how to do it, and there is much more extrema and also much more theories. So this is work in progress also, to see if one can get some minima, and also to see if this structure also gives new insights in less dimensions. So even if they are not minima, all of this can be used to construct ADS3 vacua. So I think this is very promising. Okay, we also analyzed infinite distance limits and found this web interrelating all the known and unknown theories. And this also suggests a possible new construction. So I think there's a lot of work to be done in this regard. The structure of the supersymmetric landscape carries out to a non-supersymmetric counterparts. So this motivates a classification of the non-supersymmetric possibilities, because when we have 16 supercharges, all of these theories were shown in this paper with Hector, that they are related to certain meromorphic conformal field theories, which were classified on these other papers. So this allows ones to classify all the known theories and even predict new ones. Since in non-supersymmetric we have a similar structure, in this paper last week by Hector, it's possible to see that the non-supersymmetric theories are related to these meromorphic fermionic CFTs with zeta charge 24, and they were also classified by Hona Mueller. So one can predict some new compactifications. In total, there should be 31 non-supersymmetric heterotic strings for 6D and more, and some of them seem to be tachyon-free. I think this is a nice avenue to continue. So since I'm running out of time, let me thank you for your attention.
All right, so thank you very much, Bernardo, for the very nice talk. So we're a bit tight on time, but we have time for some questions. So I think there was now a question first from the Harvard group.
Hi, Bernardo. I wanted to ask if you guys have thought about the rank 1 theories, the non-supersymmetric rank 1 theories, like Klein bottle with the bounding pin structure or stuff like that.
Yes, this is we talked about this. Let me think. Yeah, now, wait, I'm not completely sure right now if there was an obstruction. I mean, of course, so yeah, I mean, we have like some of this construction now. Like one can even, yeah, sorry, that now I know, you mean in 9 dimensions, reducing the rank by 16, and also applying an holonomy that breaks the supersymmetry.
Yes.
Yeah, I think with it, this can be done.
Okay, thank you.
Okay, there was now a question by Michael.
Oh yes, that was a good talk, especially the extended Deacon diagrams, and the animation really blew my mind. That was, I don't know how you did that. But anyway, I had a question. You mentioned about the work with Sethi, where you had the stable ADS3 vacuum, and then you stabilized silicon using flux backgrounds. You know, the way they usually do it with ADS3 cos S3 cos S3 cos S1, and that's very interesting. I was wondering, is there a way to stabilize the dilaton more in line with the way they do it for the supersymmetric theories? Like I usually use a gaugino condensate or something, and you know, create a dilaton potential. But in this case, of course, you don't have the gaugino, but we do have a lot of fermions. You know, some type of condensate to generate the dilaton potential. Because even if you stabilize all these moduli, you still have the dilaton to worry about. You know.
Yeah, I mean, in principle, for this theory, one can do this tachyonic condensation explained by this in this recent paper by Justin Cadiz and other people. but then we have this linear dilaton situation, which is not very nice. I don't know if I mean, yeah, but I mean, part of the idea is that all these theories in principle can be analyzed as the other non-supersymmetric strings, but yeah, they all have the dilaton, so in principle we have the similar situation.
Okay, all right. Well, thank you.
I think that this should be possible to stabilize dilaton this way.
Okay. all
Okay,
right.
so maybe one last question from Ivano.
All right, thank you. So first, maybe I can add like a little bit regarding the previous question. Just saying that in some cases, at least, the dilaton can be stabilized by the fluxes. Just to clear that up. But I wanted to ask. So in all of these theories, essentially, the one loop potential has an order 1 coefficient in string units, right? So how can one assess the presence of tachyons or things like that from the flat background analysis rather than the back-reacted, situation? Because naively one would expect that back reaction would be huge unless tuned by fluxes or things like that.
You mean, I mean, the presence of tachyons can be understood when we have the partition function, you can check if you have or no tachyons or not.
But that's the flat background. That's the problem, right? Like I would expect with such a huge one loop potential that the actual background, if any, would
yes, I see.
super highly curved and messy, and the actual spectrum may be wildly different.
Yeah, no, I think that should be. I mean, it would be nice to try to check how this picture changes when one considers these back reactions. I mean, I can just say that in the asymptotic limits, when one restores supersymmetry, for example, this one loop potential is very small. So at least in these regimes, all of these should stay the same. So some of the analysis here will work, but yeah, I agree that this is the classical mole space. So it would be nice to try to understand how all this picture changes when considering this. Thank you.
Thank you.
Okay, so if there are no further questions, then let's thank Bernardo and also Lorenzo once again